This is my first. Right. Thanks, Ewan. The meeting is being recorded, and so I'd just like to kick off by first saying, I'm hoping this all goes smoothly. It's my first one as the new lecturer secretary of the EGS, and I've got to say I was a bit technologically challenged with getting this Zoom up and running on my computer this evening, but looks like we've got a good quorum here. Plenty of people join the talk. So without further ado, I will go and introduce Linda, and and then I'll pass over to her to start the talk. So Linda's talk tonight is on the origin of mixed magma ring intrusions and implications for their extrusive, explosive ignimbrite equivalents in the British Palaeogene Igneous Province in the west of Scotland. It's based on her Ph.D. work, which was carried out in the 80s at Cambridge University under the supervision of Steve Sparks. And after her Ph.D., Linda's career took her overseas, first in mineral exploration and then to accountancy, but her passion for geology has always been there. And now, with retirement, given the opportunity to follow up, Linda has updated her research and intends to do more petrology and write up some more papers from her thesis, which remains highly relevant today. So tonight's talk is on a very active area of research, and your interest and questions will be very welcome. So I'd like to encourage you, if you do have a question, please type it in the chat area on the Zoom, and I'll make sure that it's shared verbally with Linda once she has completed her presentation. So I'll pass over now to Linda, and please go ahead, Linda, with your presentation.
Okay, thank you. Well, good evening, everyone. Thank you for coming tonight to this presentation. I hope you can all hear me. Good. And my name's Linda Cotterill, formerly Linda Marshall, and I'm giving this talk on mixed magma ring intrusions in the British Palaeogene Igneous Province. And this photo at the start is of the remote island of St Kilda in northwest Scotland, which will form part of this talk. All right, this is the contents of the talk. So we got the aim, the volcanic setting in the British Palaeogene Igneous Province, the structure and outcrop of the intrusions. Then we have a brief look at the net-veined intrusions in the world. Then we look at St Kilda and Ardnamurchan, which both include new research. And the missing links we're going to look at, which connect intrusions and extrusions of mixed magma. That'll be Osterhorn and Lochbar in Mull. Then we'll have a brief look at magma mixing, the petrology and geochemistry. And we'll finish off with the mechanisms of formation. So the aim of this talk is to describe the net-veined and mixed magma ring intrusions of St Kilda, Ardnamurchan and Lochbar Mull, introducing new material from St Kilda and Ardnamurchan. And as Alistair said, this was part of my PhD research, which was finalised in 1984, 40 years ago. Can't believe that. I will also briefly review similar intrusions in other parts of the world. And I believe these intrusions of mixed magma underlie many explosive mixed magma ignimbrite eruptions. I want to show how net-veined and mixed magma intrusions represent the magma reservoirs of these upper crustal level volcanoes at 2 to 4 kilometers depth, frozen in time, revealing their evolution and complex intrusive roots and tapping a chemically and thermally zoned magma reservoir. So the volcanic setting. Now, the volcanic complexes of St Kilda, Mull and Ardnamurchan and all the other complexes in West Scotland, they lie within the British Palaeogene Igneous Province, which I'll refer to as BPIP. They're part of the larger North Atlantic Igneous Province, which is shown in this map, which formed 60 to 55 million years ago. The North Atlantic Igneous Province includes West Scotland, the Antrim Plateau of Northern Ireland, the Faroes, Iceland, Greenland, and Baffin Island. This volcanism is characterized by extensive thick plateau lava flows, shallow intrusive volcanic complexes, and sill and dike swarms. This formed through continental rifting above a mantle plume and evolved as North America separated from Europe, creating the North Atlantic Ocean. Significant erosion since then has now revealed the exposed roots of these ancient volcanoes. So this map shows the location of the BPIP volcanic centres, and I will be looking at St Kilda, which is out here, which is 180 kilometres west of the Scottish mainland, and then Ardnamurchan and south of that in Mull. Okay, so these intrusions tend to be known in the literature as net-veined complexes. This term greatly simplifies them and does not adequately describe them. They are certainly complex, but the majority of outcrop is actually in the form of pillows and blobs of mafic and intermediate magma, as we see here, intruded together with a silicic magma. Because they are both evidently intruded as a liquid or crystal mush, this results in the very complex shapes, forms, and patterns in outcrop. And the predominant outcrop shown in the field is of a mixed magma intrusion. They're a hugely complicated, highly chaotic mixture of both brecciated net veining, as you can see in this photo A here, and mixed magma rocks. There's some down here, mixed magma rocks, and then in photos B and C. So because of this, many previous researchers have termed them agglomerates or breccias. I'll demonstrate this is incorrect, and they can be unravelled to reveal a logic of multiple complex stages of intrusion. They represent the magma reservoir, frozen in time, underlying the volcanic complex. So the mafic pillows, such as this one here, they're so called as they're similar to basalt lava erupted into water to form pillow lava. Except here it is mafic magma and silicic magma. The mafic pillows in these intrusions, they vary in size from microscopic clots, such as here, and streaky blobs, to many meters long and 2 meters wide. And these are all in white granophyre, which was the white silicic magma. The mafic pillows, the granophyre host of these pillows is generally coarse-grained, and it's got many druzy cavities, showing that it was volatile rich, and they especially occur adjacent to the mafic pillows. Okay, so this slide shows mafic magma pillows intruded into liquid silicic magma. The liquid-liquid states of both types of magmas is evident from the crenulate margins of the mafic pillows where they met the silicic magma, such as round here. The dark margins of the pillows show the chilled mafic margin cooled against the less hot, more viscous silicic magma. These dark margins are often full of tiny iron titanium oxide crystals, and they're free of plagioclase phenocrysts, which are often found in the coarser-grained inner cores of the pillows. In this photo, these pillows have been brecciated by a later intrusion of mixed magma, showing the explosive force of these intrusions and breaking the pillows into many fragments. So here we've got mafic pillows again in white granophyre, both intruded in a liquid state, and there's a slightly later intrusive phase has brecciated and broken up some of the pillows. So this mid-grey magma is an intermediate diorite. Such features show evidence of silicic, intermediate and mafic magmas all commingling together as liquids. So there's intimate commingling of the magmas, but incomplete mixing. Lots of tiny mafic and intermediate blobs of magma are present in the granophyre, showing chaotic, incomplete mixing taking place, both during and before intrusion. So this slide shows the intricate detail of these intrusions, and they illustrate down here, the typical brecciation features of mafic and intermediate pillows in the granophyre host magma. So we get radial fractures, we get concentric fractures in these pillows, and then we get chilled margins spalled off the mafic pillows. They all indicate the explosive nature of these intrusions. So these mixed magma ring intrusions are typically found as ring dike structures with steep outwardly dipping walls, shown here. And they're generally about 4 to 12 kilometers in diameter across. Most of the BPIP volcanic centers include at least one mixed magma ring intrusion, and this is often towards the end of the volcanic cycle. These deeply eroded ring complexes represent the exposed roots of ancient volcanic calderas formed by the successive piecemeal gradual subsidence of a central block, such as this here, along arcuate ring fractures formed above the magma chamber, such as here. Subsidence ranges from hundreds to thousands of meters, and it's usually the result of partial evacuation of the chamber, often erupting at the surface. The resultant open fractures become infilled with magma, these fractures here, solidifying to form a ring intrusion, and crushing and faulting is very common around the ring fractures. Caldera volcanoes such as these are among the most catastrophic volcanic events in the world. So I just want to have a quick look at the notable net-veined and mixed magma intrusions in the world, because they're not just in the West Scotland. And so in each of the BPIP areas in West Scotland, we've got a mixed magma intrusion in each of the volcanic centres. And we also have them in Iceland, at Osterhorn and Vesterhorn, in the Channel Islands, at Jersey and Guernsey, the Cadillac Mountain Complex, Mount Desert Island, Maine, USA. There's an Oslo complex in southeast Norway, the Jinx Island complex in Antarctic, the Mixed Magma Ring Dike complex in East Greenland, the Tastow Net-Veined Ring complex in East Kazakhstan, Mixed Magma Intrusion in East Taiwan, and the Cordillera del Paine Pluton in South Chile, and there's some granites in Southeast Australia. So you get them all over the world and all sorts of ages. So I'll now look in more detail at my research areas of St Kilda, Ardnamurchan and Loch Bar Mull in West Scotland, showing a lot of unpublished and new information. Okay, so we're moving on now to St Kilda. So this is the map of St Kilda, where I spent about 2 months in 1981 studying and mapping the Mullaig Scar net-veined complex as part of my Ph.D. research at Cambridge University under the supervision of Steve Sparks, who I'm sure you all know. So St Kilda is made up of various islands: Soay, the main island of Herta, the island of Doon, Levenish, and there's a stack up here, Borare. So this is an old volcano, most of it under the sea now. And the ring intrusion shape of it is shown by the contours of the seafloor, as we can see round here, taking in the gabbro stack up here, Borore. The purple here is the oldest intrusion on St Kilda. It's a layered gabbro intrusion, and it dips to the centre in the middle here between Herta and Borore at about 40 to 50 degrees, and these dips will dip round so that they sort of dip towards the centre, and Borore as well, that dips down to the centre. So yeah, the gabbro's been extensively dredged from the seafloor all around here. And St Kilda's unusual in having no lavas or no other extrusive rocks outcropping at all. We assume they once existed, but they've been eroded away. And there are no sedimentary rocks, no metamorphic rocks exposed. The island is located at the edge of the continental shelf, which is believed to be composed of Precambrian Lewisian gneiss at depth, and Lewisian pebbles have been dredged up from the sea floor. And this St Kilda volcano is located at the junction of ancient crustal fractures. There's a major northwest-southeast shear zone, and that intersects with tensional faults which trend northeast-southwest and north-south. So northeast-southwest is the main sort of fault trend for St Kilda. Right. This is a simplified geology map of St Kilda, and I've excluded all the faults on here to simplify matters. And this is based on BGS work by Harding et al., mapping in 1978 to 79, and modified by my Ph.D. research, 1984. So the main faults, they trend northeast-southwest this way. And the earliest intrusion, as I've said, is this gabbro, layered gabbro intrusion shown in purple, which is, it was thought to be a ring dike, but I think it's more likely to be a sort of funnel shape, given the sort of gentle 40 to 50 degrees dip towards the centre of the volcano. And this gabbro was intensely sheared and recrystallised before intrusion of the net-veined complex, which is this sort of taupe colour here. And the shearing is probably related to gradual piecemeal subsidence of a central caldera block, which resulted in this mixed magma intrusion. So the net-veined intrusion is approximately 2 kilometres from the outer gabbro wall here to the inner margin here. But the inner margin is actually formed by this young conifer granophyre, which truncates the inner margin, so we don't have really any information about that. The net-veined intrusion actually consists of 4 phases of intrusion, and phase 1 and 3 are the main events, but they all result in highly complex, chaotic, cross-cutting outcrops. The outer walls of the net-veined intrusion, they dip steeply outwards 80 degrees. You can see here. And this wall can be clearly seen in many places. And we have pieces of the gabbro roof pendants along here, which have remained in situ. And they suggest that a central gabbro block subsided along here in the centre of the volcano to enable intrusion of this net-veined complex, and the rest of the horizontal gabbro roof was then eroded away. So the conifer granophyre, which is in pink here, that's the youngest intrusion on St Kilda, and that, as I said, that truncates the inner margin of the net-veined intrusion. the outer gabbro, that's been dated at around 60 million years, while the youngest Conica granifer in pink, that gave an age of 55 plus or minus 1 million years. So I think the rocks would probably benefit actually from more efficient up-to-date dating, so they can be better compared with the other Hebridean volcanoes, because I think these dates go back to the 80s. Okay, so I'm still looking at St Kilda. Now, many of the best exposures of the net-veined intrusion are on the very steep cliffs, and exposure is really excellent here once you get your eye in and you have to use binoculars. So this slide shows a cliff section on the southwest side of Herta, the main island, and it shows all 4 phases in the cliff face here, with the outer layered gabbro wall down here bounding the net-veined intrusion, and this is the gabbro outer wall as well up here. So this is the geology of this particular area. We have the gabbro outer wall in this dark blue, and we've got roof pendants overlying the net vein complex here. And here we've got the 4 phases rather of the net vein complex. We've got phase 1, which is this bright green. We've got phase 2, which are these minor granifier sheets in red. All this taupe is phase 3, which I'll explain later. And phase 4, we have granifier sheets, which are these tiny little purple things, sheets and dikes over there. Okay. So this is the dune cliff section. So it's an excellent exposure between the Isle of Doon, which is here, which is full of puffin burrows. It's an amazing place. And the main island of Herta on the right. So we've got this steep cliff section, which is fault controlled. And it's a superb cross-section slice through the mixed magma ring intrusion. So we'll look at that in more detail in the next slide. All right, so this is the dune cliff section. This is what we've just been looking at the top of. So this is the entire thing. And this is my geological interpretation. And it's 220 meters from the outer part of the cliff here to the gabbro wall. So from here to there. So the gabbro wall is this part here. This is the contact in black. And the steep outer gabbro wall, this is the net vein complex here. So the steep outer gabbro wall is a good solid contact. There's no brecciation in it, only a minor late mafic dike which intrudes it. And it reflects the violent explosive nature of the mixed magma intrusion. So it's all directed upwards towards the surface. So in this net veined intrusion, we've got phases 1, 2, and 3. The lime green is phase 1, and this consists of large rounded diorite pillows in granophyre. Phase 2, in pink, it consists of elongate flow-aligned mafic pillows in granophyre. And phase 3, in the pale brown, that consists of large elongate mafic and intermediate pillows, again all in granophyre. So phase 1 is cut by phase 2 and 3, so only parts of the earlier phases survive. And phase 2 here, this sheet, is the common feature of phase 2 and 4, that you get sheets that widen upwards. They're all sort of funnel shaped. All right. So this is an enlarged part of the dune cliff section that we've just been looking at. It's near the sea level. This is the sea down here. And this shows phase 3, which is the main phase. And you've got very elongate diorite pillows here in white granophyre. So the pillow in this upper centre bit here is many meters long and about 2 meters wide. And note how it breaks up and becomes bulbous over its length in the granophyre magma, like in a lava lamp. You have the impression of the mass of granophyre and mafic pillows streaming upwards, channeled by the walls of the intrusion. And these elongate pillars are approximately parallel to the outer wall. And there's also a late mafic sheet at the base. Okay, this slide shows features similar to lava flowing into water, except these are of mafic and intermediate magma flowing into silicic magma. They're all liquid or crystal mush at the same time. And there's so much more mafic magma than silicic magma. It's superheating the silicic magma and making it much less viscous. And this in turn affects the billowing mafic magma pillows, such as here with these elongate pillows. They become bulbous, then they break up at the narrow necks to form smaller rounded pillows, such as here. And other pillows break up along joints. And you also get situations where you get the flow sort of breaking through like the chilled margin to form various different chilled margins, just as you do in like pillow lavas in water. Right, I'm still on St Kilda. Got the top slide up here that shows partial melt textures in phase 1 diorite pillows in granophyre, with some very pale pillows below, which are likely hybrid magmas, these blobby things down here. The middle slide shows brecciated diorite pillows in granophyre. So this was sort of one pillow originally, and it's sort of broken up into sections. And as diorite's an intermediate magma, it's closer in composition and physical properties to the silicic magma. So the contacts between the two magmas tend to be more blurred and also coarser grained as compared to the mafic silicic magma contacts. This bottom slide, it shows the contact of phase 1 on the left here, which are large diorite pillows in granophyre, and phase 3 on the right, which is shown in a close-up on the right here. And these are huge elongate mafic pillows in granophyre. And some of these are what I called pillow dikes. They're embryonic dike intrusions, which are broken up in the silicic magma into smaller pillows, as it could not maintain its coherent dike shape during intrusion in silicic crystal mush. I've been able to construct some exciting cross sections of the St Kilda net-veined ring intrusion, and this is one of them. So this is from the southwest to the northeast. It's quite close to the dune cliff section. So this is approximately 2 kilometres wide from the Gabbro wall here to the Conica granophyre, which is the youngest intrusion and cuts the net-veined ring intrusion on its inner margin. So you can see that the pillows which form the intrusion at deeper levels, they merge from elongate pillows in granophyre to more rounded pillows to net-veined rock up here, which is mafic rock net-veined by granophyre magma. And this is where the mafic magma had partly solidified close to the gabbro wall when it was intruded, sorry, the gabbro roof, before brecciation by silicic magma. Phase 2 and 4, which are the minor phases on St Kilda, they're minor sheets and dikes such as these here and here, and they consist of granophyre containing smaller elongate mafic pillows, which tend to be flow aligned parallel with the intrusion walls. I just want to mention too that, as it says here, the pillows in this cross section, they're all schematic. They're not to scale at all. So it's impossible to do that, obviously. These minor intrusions, you will see later on in the talk that they're similar to the Lochbar felsite ring dike on Mull, except I think they're at different crustal levels. St Kilda's at a deeper level and Lochbar at a shallower level. Right, now we move on to Ardnamurchan. So this is from the Edinburgh Jolsock Ardnamurchan Field Guide 1976, and cone sheets and dikes, they're all excluded for simplicity. So we've got the centres 2 and 3 of the ring complexes shown here. The centre 2, the old volcanic complex, is here, and centre 3 is here. And they both have net-veined ring intrusions in them. In the centre 2, it's this dark green 2C ring intrusion round here, which has intruded into this 2A, this hypersthene gabbro ring intrusion, which is the first ring intrusion of centre 2. And on its inner margin, it's cut by a number of other gabbro ring intrusions. So again, you can't see what the inner contact is like on the net-veined intrusion. And the net-vein ring intrusion in centre 3 is this bright orange thin intrusion round here, which is 3B. And the ring intrusions in this index, they're both noted as being quartz dolerite with granophyric granite, centre 2 and centre 3 there. I wanted to say that the centre 3 here, it has a magnificent ring of, the gabbro ring intrusions around here form a magnificent ring of hills around the exhumed volcanic centre. So you get a wonderful feel of being in the centre of the volcano when you're situated near a place called Aknahar in the centre of these ring intrusions. So if we go back to centre 2, this 2C here, there have been at least 3 phases of intrusion in this net-veined ring intrusion here, and they've all been intruded in a very short period of time, so none had cooled and solidified before the next mixed magma intrusive phase. So we have an early outer ring of porphyritic dolerite, which has chilled against the hypersthene gabbro ring intrusion on its outer edge. And this is followed by an inner ring of apheric dolerite. And this is followed by widespread invasion of silicic sheets and net veining into the mafic rocks, all while still a crystal mush. And the silicic magma was charged with abundant pillows and liquid clots of mafic and intermediate magma. And from mapping, I identified a northern zone up here in this centre 2 intrusion, which is mainly net veining, and a southern zone down here, which is mainly pillows, mafic pillows in granophyre. Right, these on Ardnamurchan Centre 2, they show the brecciated gabbro roof overlying the net-veined intrusion. So this exists as a roof pendant here, overlying the net-veined intrusion down here. And it's shattered by the intrusion of the net-veined complex. So it's indicating that the net-vein complex was intruded at a shallow crustal level, maybe 2 to 4 kilometers depth. And in West Ardnamurchan, the Gabbro ring dike is also roofed by basalt lavas, again indicating that the net-vein complex was emplaced at a subvolcanic crustal level. This shows the a close-up of the brecciated Gabbro roof from this roof pendant up here. So in Ardnamurchan Centre 2, gravity surveys indicate a Gabbro cylinder form underlying the volcanic complex, which would be equivalent to the ancient crystal mush magma reservoir. And they indicate it's 12 kilometers in diameter and about 4 kilometers deep. So it's much smaller than the Skye volcanic centre. Some of the Gabbro ring intrusions on Ardnamurchan have a fluxion structure due to the alignment of plagioclase phenocrysts. And if this is due to magma flow in the crystal mush state, it implies these wider Gabbro ring intrusions are perhaps funnel-shaped, which I feel is more likely. So we could foresee perhaps this structure evolving with time into a piecemeal caldera collapse towards the funnel centre, leading to the violent net-veined intrusion. So I divided the Ardnamurchan net-veined complex into a southern pillowed zone and a northern net-veined zone. So the southern part of the ring intrusion, which is shown in A, B, and C on here, it contains an assortment of porphyritic and apheric dolerite and diorite pillows in granophyre, which were all liquid or crystal mush when incorporated into the silicic magma, forming chilled crenulate margins against the granophyre, as here. The northern part of the intrusion, close to Sanna Bay, is dominated by joint-controlled granopheric net veining of porphyritic dolerite, as shown in this photo D here. And here the ring intrusion had solidified and cooled more before silicic magma brecciated it. So I believe it's possible that the entire caldera block was tilted and subsided more in the south, while still attached to upper levels in the north. The intrusion actually tapers out in the north, along with many crush and shear zones associated with piecemeal caldera subsidence. So this is consistent with this scenario. So this is my interpretation of a cross-section from south to north across the southern pillowed zone of the Ardnamurchan net vein complex. From mapping, I identified an early outer ring dike of silicic magma with lots of rounded porphyritic dolerite and diorite pillows. And this is bounded by the early Hypocene Gabbro ring intrusion. And then before the porphyritic dolerite had cooled and solidified, we had a ring intrusion of granophyre containing elongate apheric dolerite and diorite pillows, as shown in green here. So this forms the bulk of the pillowed zone in the south. And these pillows, again, they're schematic, they're not to scale at all. But, sorry, some of these pillows, these mafic pillows here, they can be meters long, 2 to 3 meters wide, so some of them are very large. And the apheric dolerite in granophyre is cut by these younger ring intrusions here, these mostly quartz gabbro ring intrusions. So again, we don't have any information on the inner contact of the net-veined intrusion. Interestingly, these elongate pillows in granophyre here, they tend to flow parallel to the overlying roof pendants, these gabbro roof pendants overlying the net-veined intrusion. So it suggests there's some sort of flow alignment as the intrusion was emplaced in the rocks. Right. I hope this isn't too confusing for everyone. This is an outcrop in the field of what I've just been discussing. This is in Ardnamurchan Centre 2. It's in the southern pillowed zone, part of the net-veined ring intrusion. And the photo shows these large apheric dolerite and diorite pillows in white granophyre magma. The pillows are horizontally elongate, meters long, and about 2 to 3 meters wide. And some of these pillow zones grade into net vein zones up to 200 times 300 meters in size. The pillows are flow aligned parallel to the overlying gabbro roof, which is also net veined by granophyre, showing that the roof was brecciated by the violent intrusion. And you get many angular gabbro xenoliths broken off the roof, lying in the silicic magma. Diorite and dolerite pillows seem to be randomly distributed. And the granophyre everywhere in this net-veined intrusion is full of tiny chilled blobs of mafic magma. And these hot basalt magma blobs heated up the silicic magma, greatly lowering its viscosity and increasing its temperature. So each 100 degrees centigrade rise in temperature results in a 10-fold decrease in viscosity of the silicic magma. So this can lead to dramatic explosive eruptions. Right, the Ardnamurchan Centre 2 net-veined intrusion has the structure of a steep-sided ring dike, seen as a partial ring from the air, with a number of sheet apophyses coming off the outer sides of the ring dike. So it's quite an unusual structure, and this shows one of the sheet apophyses. So this connects to the left with the main ring intrusion. So we had mafic magma intruded first in the net vein complex, chilled against the gabbro wall and the roof. Then this was followed soon after, before it had cooled and solidified, by silicic magma charged with masses of liquid blobs of mafic and intermediate magma, sometimes breaking through at the surface as violent mixed magma eruptions. And these sheet apophyses are net veined with silicic magma close to the ring dike. But you get abundant silicic magma with mafic blebs found in these outer extremities. So within the ring dike, the silicic magma seems to be concentrated upwards and outwards, suggesting an intensely violent intrusion and eruption. And I've included this cross-section down here. This shows the elongate mafic pillows in silicic magma down here. But sometimes you can see it in cross-section at right angles to that, and you can see that the pillows are actually more sort of cigar-shaped because they have sort of rounded cross-sections to them. That gives us sort of an insight into the intrusion. So in the northern net vein zone of the Centre 2 Ardnamurchan intrusion, we often see areas in cross-section with a complex, intricate network of interconnecting silicic sheets and dikes. So this silicic magma is everywhere charged with abundant small clots of liquid mafic magma. The silicic dikes are like pipes that connect up and down to sheets on many levels. Dimensions vary from a few millimeters to around 2 meters. And such unusual pipe networks have also been reported from the Guernsey net vein complex and also at Slieve Gullion in Northern Ireland. Right, this is the Centre 3 net veined ring intrusion of Ardnamurchan. This is one of the last events of Centre 3. This is the Ardnamurchan Peninsula here, and it's the black intrusion round here. And it was intruded into the eucrite or hypocene gabbro ring intrusion as a narrow, steep-sided dike, shown here, and it's 150 meters wide. And it shows that the mafic magma was intruded first, chilled against the gabbro wall, and this is quickly and explosively followed by silicic magma, heated up and made less viscous by being charged with abundant tiny mafic magma clots. And this brecciated the dike margins along there, veined the gabbro wall in places, and then solidified as a mixed magma intrusion. And it's very likely that this also erupted at the surface as a violent mixed magma eruption, similar to the violent Askja and Hekla eruptions in Iceland. This one may be a smaller, deeper level, intrusive equivalent of the Loch Bar felsite ring dike on Mar, which we will look at shortly. Right, these thin section photos show hybrid magmas from St Kilda. So we have a leucodiorite up the top with a heterogeneous texture due to many clots of mafic and intermediate magma in silicic magma, and a melodiorite below. The thing I want to emphasize is that in thin section, all the rocks from these net-veined intrusions show abundant evidence of magma mixing on the micro and macro scale. The hybrid magmas are commonly recognized by their disequilibrium phenocryst assemblages. In these rocks, we see reverse oscillatory zoning, resorption of plagioclase phenocrysts, calcic anorthite zoning more sodic compositions, indicating injection of hot mafic magma into silicic magma and heating the lower temperature silicic magma. In St Kilda and Ardnamurchan, xenocrysts are found in all the rocks of the net-veined complexes. Those normally found in granophyre, such as alkali feldspar, are found abundantly and widespread in dolerite and diorite, and calcic pyroxenes and plagioclase, normal in dolerite and diorite, are found everywhere as xenocrysts in granophyre. This all suggests the violent convection and mixing of magmas, both within the magma reservoir and during intrusion and eruption. Right, now I want to look at missing links. These connect intrusions to the mixed magma intrusions to the mixed magma extrusions. So we're going to look at Osterhorn in Iceland, the Lochbar ring dike Marl, and also recent research on Skye, Marl, Arran, Northern Ireland, Rum and Egg. So they each provide a link from the mixed magma intrusions to the mixed magma extrusive volcanic rocks. So the first missing link in this story is the Osterhorn net-veined intrusion in southeast Iceland. These are some of the photos from Wiedendorfer et al. 2014. They show chilled crenulate margins of the mafic magma against the silicic magma, which is brecciation of pillows of mafic and intermediate magma in silicic magma. And the silicic magma is also full of tiny little clots of mafic magma chilled against the silicic magma. All the same features as at St Kilda and Ardnamurchan. The Osterhorn intrusion is much younger. It's around 6 million years old. It's a mixed magma stock-like structure emplaced in Palaeogene lavas and surrounded by gabbro. And there's also a related caldera at the surface. So this image is from the book Iceland Classic Geology in Europe 2022, shows the connection between the Osterhorn net-veined complex and the Skesser-Tuff ignimbrite. Basalt magma has replenished a rhyolite magma reservoir from depth and heated it up, reduced its viscosity, and remobilized it upwards. This led to volatile loss and extreme vesiculation up the feeder pipe, a Plinian eruption of mixed magma blebs in a rhyolitic ignimbrite, finally collapsed to a pyroclastic density flow. This connects the net-veined intrusion at depth to an extrusive event, which is still seen in outcrop. Our second missing link is the Lochbar felsite ring dike on Mull, which is shown here in red, and it's considered the most perfect ring dike in the world. It's intruded into Glen Cannel microgranite. So in this diagram, the felsite ring dike encloses a caldera or sunken block here, whose subsidence produced arcuate ring fractures into which the felsite ring dike was intruded. This was accompanied by a violent mixed magma eruption at the surface. The diameter of the ring dike is 5.8 kilometers this way, 8.5 kilometers that way. And the width varies with a maximum of about 300 meters. This is thinner than the net-veined intrusions, which are typically twice this width or more. So this is the Lochbar felsite seen in outcrop. So we have a silicic magma, which is the paler rock here, containing abundant basaltic andesite streaks, bands, and inclusions, many of them contorted and flow-banded, showing their plastic nature during intrusion in the silicic magma. The flow banding is generally parallel to the outer ring dike wall. This is an intrusive ignimbrite with contorted fiamme and probably also erupted at the surface as a violent Plinian eruption and a pyroclastic flow, just like the Skesser-Tuff ignimbrite in Iceland. However, now nothing remains at the current surface of any extrusive rocks which can be linked to the Lochbar felsite. These fiamme are comparable with the mafic pillows and inclusions in granophyre in net-veined intrusions, but the Lochbar intrusion is at a higher crustal level than the net-veined intrusions. The flow banding in the felsite is comparable with the elongate mafic pillows in granophyre. I would suggest that a net vein complex would underlie the Lochbar ignimbrite. These show the Lochbar felsite in thin section. So in photo A here we have a vesiculated andesite contorted inclusion. So this is the inclusion here, and it's in the felsite or silicic magma. So these are collapsed bubbles here in white and shards. So it's the former sort of vesiculated pumice. And the black in this inclusion is andesite glass, chilled against the cooler felsite magma. And photo B below shows interbanded black glassy andesite and paler silicic magma, sometimes draped around resorbed phenocrysts of ferrohedenbergite and iron-rich clinopyroxene and orthoclase. Note the paler silicic magma contains masses of tiny disrupted andesite inclusions, which would have heated up the silicic magma, leading to the violent mixing and eruption of the two magmas. So the third and final missing link in this story, there's been an abundance of recent research reinterpreting agglomerates and other volcanic rocks in the BPIP in Western Scotland as extrusive ignimbrites. This slide summarises some of them. So we've got Ardnamurchan Centre 1, Ben Hyant area, that's Brown, July 2024. The Mull Lochbar Caldera infill, Nichols, September 2024. Arran, Gooday, December 2024. Skye, the Kilchrist area, Drake 2022. Egg, Troll 2019 and Brown and Bell 2013. Rum, Troll 2018, Holohan 2009, and Slieve Gullion in Northern Ireland, Stevenson 2008, and Bell and Emeleus 1988. And many discuss how silicic extrusive rocks may well have been much more abundant in the Hebrides than the actual outcrops seen. This is my view too. Such rocks are often preferentially eroded away due to their lower resistance to erosion, and often only small outcrops remain dropped down into the caldera. My fieldwork leaves me with the impression that silicic volcanic rocks were much more abundant in these areas than current outcrops testify. In particular, the net-veined intrusions may have vented to the surface a huge amount of silicic magma now eroded away. The mafic pillows in silicic magma in these intrusions may have settled amongst each other, squeezing out a lot of their former silicic magma host. So I think we're coming to realise that the BPIP volcanism in West Scotland was more violent and explosive, and that silicic volcanism was much more widespread and common than previously realised and documented. Right, it's just a brief overview of the geochemistry on St Kilda and Ardnamurchan. These net-veined complexes all include a wide range of highly evolved magma compositions, from basalt, ferrobasalt, basaltic andesite to rhyolite. During my research, I did a geochemical analysis of a wide range of rocks from St Kilda and Ardnamurchan, covering major trace element, rare earths and strontium isotope data. And this is just a brief review with iron oxide on the vertical axis and MgO on the horizontal axis. And there's St Kilda on the left and Ardnamurchan on the right. And the geochemistry basically shows that most of the rocks are related by fractional crystallization, which is shown by the red trends here for St Kilda and here for Ardnamurchan. And they're close to the iron enrichment trend of Thingmuli in Iceland, which is the blue trend there and there. But there are also many rocks which appear to be hybrids in the field with a heterogeneous texture, which are actually hybrids on these graphs, and they fall into these fields here and down here as well. These are all hybrids. So you get a huge amount of mixing of all sorts of rocks. And other geochemical evidence suggests that the silicic magma in these complexes is predominantly from partial melting of older basement rocks, as in the other Hebridean volcanoes. Right, that's just a brief. Sorry, this is the last slide. So, this is an attempt to illustrate how the intrusions of St Kilda, Ardnamurchan and Lochbar Mull ring dikes evolved. And I've tried to put in the current level of outcrop. This is St Kilda and Ardnamurchan here, so it's sort of round about the Gabbro roof, whereas Lochbar ring dike marl. It's at a higher level. So there's a wide range of highly evolved magma compositions in these, from basalt, ferrobasalt, basaltic andesite to rhyolite. And I've attempted to show a sort of a zoned magma chamber here with the zonation going from mafic to felsic. And this wide range of magmas is intimately associated in these intrusions. It's either commingling as pillows in silicic magma, or it's more mixed as hybrids. And you get a large number of different phases of intrusion and eruption. It's generally agreed they originate like their mixed magma ash flow extrusive equivalents from these chemically and thermally zoned magma reservoirs at a shallow crustal level, 2 to 4 kilometers depth. So we envisage that you have an open system with multiple replenishments from below of basalt magma, triggering mixing and violent eruption, intrusion and eruption at the surface. And they demonstrate the complexity of interconnecting and cross-cutting mixed magma dikes and sheets in magma chamber evolution, and their connection with violent explosive mixed magma eruptions. The complex, intricate network of sheets, dikes, net veins, and pillow dikes in these intrusions provided channelways upwards and laterally for the wide range of magmas to commingle and erupt at the surface. The net vein complexes represent the frozen roots of these shallow mixed magma reservoirs. I believe they're more significant and probably more fundamental to volcanism than previously realised. So I now intend to publish this work on St Kilda and Ardnamurchan. There were 2 joint papers out with Steve Sparks in 1984 and 1986, but there's still a large amount more to be published. Now I am retired, I'm in the process of completing this work. Thank you.
Thanks very much, Linda. And I've got to say, it's a very complex subject, and you've done a great job in explaining some of it to us tonight. So there was a comment in the chat box, so I'd like to encourage, if anybody's got a question, please type something in, or just say, I've got a question, and Ewan will unmute you so that you can ask it. But so I do see a question from Graham here. So Linda, Graham, thanking you for the talk. And is it known what the source of the acidic felsic magmas is likely to be? Crustal rocks melted at depth by interaction with the mafic magma chamber. Does the composition of the granifier vary in detail from one complex to another, perhaps indicating variability in the source rocks available for melting?
Most of them seem to be mainly from the partial melting of the Precambrian rocks. There's Lewisian gneiss in St Kilda, deep down, and the Moyne rocks in Ardnamurchan. I think there's also a sort of some element from the fractionation of basalt, the basalt magmas as well.
Thanks, Linda. I've got a question myself, just in case, whilst others might be typing in. You showed some beautiful rock textures of brittle behavior, the fracturing of some of these more mafic lava intrusions, and the clearly liquid textures there. So my question to you is related to the temperature difference between the mafic and the felsic. Are the things that got brittle structures in them and the fractures, are they likely to have been the early bits of mafic intrusion, which chilled rapidly when they met the felsic magma, which is much cooler, and therefore solidified. And the stuff that's showing the pillow shapes and the sort of burst pillows that you showed, are they likely to be later when the felsic magma has been more superheated?
Yes, I mean you seem to get a pattern where you get mafic magma always coming in first, and it chills against the gabbro roof and the walls, and then the granifier comes in, and so where you've got the mafic magma at higher levels, it's solidified more, and so it's brecciated when the silicic magma comes in, and yeah, you tend to get more sort of pillow shapes at depth where you've got hotter magma.
Thank you. So, anyone else with a question for Linda? Well, if not, I'll keep an eye on the chat if someone is typing a question in. Oh, here we go. We've got one from Simon Cuthbert. His question is, once a rhyolite melt mass has developed, I wonder if it acts as a filter that prevents basalt erupting, with rhyolite erupting instead. The higher density of basalt melt and chilling and resulting increased rigidity of the basalt will prevent it rising further. Does basalt not get to the surface so much due to this?
Well, I think the basalt's actually helping the silicic magma to get to the surface. There's so much basalt and intermediate magma, and it's heating up all the silicic magma and making it much less viscous, and it's just vesiculating, and because they're very volatile rich, the acid or the silicic rocks in these intrusions, and you get a lot of pegmatitic areas as well in them. So I think it's you've got a lot of vesiculation going on of the granifier magma coming up the intrusion, bringing the mafic magma with it. So I think the basic magma is actually helping the silicic magma to reach higher levels than it normally would.
But does the basalt itself manage to get in large volumes to the surface too, along these complexes?
It only seems to sort of, as it does in the mixed magma sort of volcanic rocks, where you just get little blebs and streaks of it.
Okay.
So I think that the basalt magma is sort of helping the silicic magma to get up, because it's passing all this heat across, and it's massively decreasing its viscosity, and it's superheating the silicic magma. But I don't think you get a huge amount of sort of basalt actually erupting at the surface. You just get these sort of blebs, as I said, blebs and streaks.
Thank you. Okay, well, I don't see any other questions coming in, but Zoom, I've got to say, it's not like WhatsApp where you can tell by some dots bubbling along that somebody's typing. So
Yes.
there might be a question, and if it pops up, I'll read it out to you. But I'd just like to say thank you very much, Linda, for a fascinating talk, and one which clearly indicates there's more to be done in this space. And it's I wish you great success with your future studies and research here. And I think your link there with the Iceland eruptions just makes it so topical today. That the rocks we've got in the BPIP could have a lot to learn from what's going on in the present day, and I may have things to share from the subsurface sections effectively we see in the exposures in northwest Scotland. So I wish you all success with your future studies. And,
Thank you.
you know, and we look forward to maybe sometime in the future getting an update on this story. And
yes, I hope so, and in person as well.
Yeah. No, thanks. I mean, this is the first all Zoom talk I've been to for the EGS, and I think it's gone very well. I hope, I mean, if anybody's got any other feedback on how the talk went today in terms of the methodology, not the content, please share that with me, because if we have another Zoom only one in the future, we'd like to learn if there's anything we can do to improve it. But once again, I mean, we can't give you a round of applause so effectively here, Linda, but please accept from me a virtual round of applause from the Edinburgh Geological Society. And thank you so much for your talk. And
okay, it's a pleasure.
There's a number. Oh, some people are being able to show clapping going on there on their screen, but
oh right.
And there's some wonderful.
Oh yes, I can see. Yes.
And if you open the chat window, you'll see some wonderful compliments coming through on the chat box as well. So,
oh, lovely.
Thanks again, and
okay.
We'll see everybody at the next lecture in person, hopefully on the 29th of January in the King's Building.
Okay.
Thanks everyone for attending.
Thank you very much.